Today we will start off with the concept of thermal properties of matter. And it's actually a very easy chapter. A lot of people tend to ignore these kinds of chapters. Like in grade 11, I've seen a lot of students are focused more on the first half, laws of motion, rotation, gravitation, work and energy. But the second half is also very important, as well as it is easy. So if it is easy, then it is also scoring at the same time. So you should not ignore these chapters. It's very important. Now, thermal properties is a very easy chapter. So that's why you should actually cover this up as well. Then your chances of attempting the question increases. So let's start. In thermal properties of matter, we will start off with a very easy concept, which is of course heat. So what is heat? It is basically a form of energy which can be transferred from one place to another depending upon the temperature. So keep it in mind. There is a very small difference, but very important difference between heat and temperature. That heat is simply energy, whereas temperature is a degree of hotness and coldness. Basically, how hot or how cold a body is, that is temperature, whereas heat is what? A form of energy. SI units, we measure heat in joules because it's energy. SI unit for temperature is Kelvin. So it always moves from a hotter area to a colder area. And when you increase heat, temperature increases. When you decrease heat, temperature decreases. So this was a very basic thing, but this was very important at the same time, because a lot of people don't know the simple difference between heat and temperature. Now, just like we have yeah, so just like you have learned about the expansion or thermal expansion in smaller grades, we are going to continue that only. What is that? Basically, whenever you increase the temperature, whenever you heat a particular body, the size of the body actually starts increasing. There are multiple examples of it. The length of the railway track increases when it's too hot. Yeah, sometimes the road are like this, or if you will not make proper gaps in road as well, they might go like this because they were expanding and they had no place to expand. Same for liquid as well. If you heat a liquid, it will expand. So this is known as thermal expansion. Very simple, very easy. Now, there are majorly three types which we are going to discuss. First is the linear expansion, which happens in railway tracks. And what do we call? The mercury, which is there in a thermometer, is one of the example for that. Next is a superficial expansion. The area, or what we can say, that whenever the area of a body expands, that is superficial or aerial expansion. That's why you will see that when we actually install glass, why is it not a single glass all the way? Why are you making so many glasses and then adjusting them? Because it will expand, and when it will expand, you need to leave some small gaps so that it is not cracking down all the way. Okay. And the last thing is, of course, cubical expansion or volumetric expansion, when the volume of the body increases. This is one of a very good example for that. So this ball very easily passes through this ring, but if you increase temperature, the volume also increases, then it actually gets stuck over here. So this is a very good example of how the volume of a body increases. Okay. So basically by increasing the temperature. Now let's try making the formula. We will be making a formula for the coefficient of linear expansion. What is a coefficient? Basically, it's a number which is different for different types of metals or whatever basically you are using. You will see it's a different number for all of them. Why? Have a look. First of all, the increase in length or the change in length of a body depends upon the rise in temperature of the body. Okay. So it depends upon the rise in temperature. The more temperature you will change, the more length you will see to be increasing. And then the increase in length is directly proportional to original length as well. So bigger the length of the body, the longer expansion you will see. Now, when you combine both of them, of course, by removing proportionality, you will get a constant, and this constant is what we call as coefficient of linear expansion. Now, there are three ways by which you can actually make the formula, but I personally prefer this one. That is, alpha is equals to the increase in length, that is delta L, divided by original length, which is L, multiplied by rise in temperature, which is delta T. So this is the best way actually. Now, the same formula can be applied in three different ways, as you can see over here. That is alpha, beta, and gamma. So if I am talking about length, then that will be like coefficient of linear expansion. Then, or I can write it down, coefficient of linear expansion. Then when the area of a body is increasing, then there is beta. This is coefficient of superficial expansion, superficial expansion. And last is gamma, which is volume, which is actually what? Coefficient of what we can say, cubical expansion. Okay. So this is the coefficient of cubical expansion, or you can say volumetric expansion. All the three formulas are actually in the same manner. That is, increase in dimension by original dimension into rise in temperature. That's it. You can see increase in area by original area into rise in temperature, increase in volume by original volume into rise in temperature. Same thing happens three times. Okay, it's not different at all. That's it. Now, all the questions in this topic will be very similar, very easy at the same time. So you don't have to worry about it. But one question which I want to discuss, it's kind of a topic. Yeah. So let's discuss it. So I am explaining you a question, but take it as a topic. A clock with the iron pendulum keeps correct time at 20 degrees Celsius. How much will it lose or gain if temperature changes to 40 degrees Celsius? Of course, as you clearly know, that time for a pendulum depends on this factor 2 pi root L by G. Now, clearly you can see that when you are increasing the temperature, when you are changing the temperature, then automatically length will change. When length will change, the time will change at the same time. So we need to do something in such a way that we are able to find out how much variation in time is there. So when the temperature is what, 20 degrees Celsius, then the time period is 2 seconds. When the temperature is what, 40 degrees Celsius, then we have to see the time period. So clearly I can apply this, that if at 0 degrees Celsius, if this is the length, then at 20 degrees Celsius, this will be what, 1 plus 20 alpha. And similarly, when I'm talking about at 40, I will do what, 1 plus 40 alpha. Yeah, it is actually the same formula coming in a different way. That is, alpha is equals to what, change in length by original length into change in temperature. Okay, so the same formula is written over here like this, that if I want to say that delta L, it will be what, alpha into L into delta T. Delta L means what, L40 minus L0 equals to how much? Alpha into original length. So original length is 0 degrees Celsius and temperature is how much? It will be like this, 40 minus 0. So you will see that L40, L0 will go over there and you can take L0 common. It will be 1 plus 40 alpha. Yeah. So this is how we are making it. That's why I'm saying you that try to remember this formula. All of the other ones you can easily make, very easily. Yeah. Now, as you know that the time period is equals to 2 pi root L by G for 40 degrees Celsius, for 20 degrees Celsius, these will be the things. And of course, if you will take the ratio of them, so ratio will also be very easy, which is this to the power 1 by 2 and this to the power minus 1 by 2, because you are also going up. So when you are going up, power becomes negative at the same time. After this, we will use binomial theorem. So this is why I'm talking about this question, because this is not a very usual straightforward kind of a question. If you know binomial theorem, good for you. If you don't know, what do? We take 1 by 2, we multiply it over here. We take minus 1 by 2, we multiply it over here. And that's why we get 1 plus 1 by 2 into 40 alpha, 1 minus 1 by 2 into 20 alpha. Now you will think that why are we doing it over here? Why can't we do it everywhere? No, you can't do it everywhere. You are allowed to do it in only the places where the power, or you can say this particular value, is kind of small. So already the value of alpha is small, and if you will square it, or if you do power 3, power 4, power 5, they will become even small. So that's why we can neglect those values. If you understood it, okay. If you don't, you can say right now we can use it. And after that, the question becomes solvable. Because if you want to calculate the fractional loss in time, it is what? 40 minus 20 by 20, which is equals to 10 alpha. This is what you can do to get your answer. That's it. That's it. You don't need anything else. That's it. Yeah. Now, there are a lot of questions which I have mentioned over here. You don't need to go through all of them, like especially this one you don't need to do. But this question and this question, please have a look onto it. Very, very important. Yeah. Now, next is specific heat. Now, defining specific heat is a very easy task. Why? imagine you have a pressure cooker which is empty. Nothing's there in that pressure cooker. Although I'm not recommending you to do something like this on your own because it's dangerous. But uh, if we have a empty cooker, and if we have a cooker with water inside, and we are trying to heat up both of them, so if I want to heat this, it is very easy to heat. Whereas if it is having water, it will not heat up that quickly, or you can say it will take more time, take more energy to get heated up. This is what we call as specific heat, that because it is getting heated up easily, it is having a small specific heat. It will take a lot more time. That's why it is having a bigger specific heat. So what is specific heat at the end? If I want to define it, it is simply the amount of heat which is required if you want to raise the temperature of a body, if you want to increase the temperature of a body, if the mass of the body is m. That is, delta Q is heat, delta T is temperature, and m is the mass. Very important. So usually this version of the formula is more used, so you can remember this one, but at the end both the formulas are same. Now this is specific heat. I can also explain molar specific heat in the same way. What is molar specific heat? If I am talking about a given number of moles, what we were doing over here, we were talking about a given amount of mass, then it was specific heat. But when we talk about given number of moles, it will be molar specific heat, which will be equals to what? Nc delta T. Okay. Now, next thing which I will be explaining you, which is known as heat capacity. But when you will read the concept of heat capacity, you will feel like that it is the same thing as specific heat. That is, it is defined as the amount of heat required to raise the temperature through 1 degree. What is it? Like, again, the same kind of definition. The same definition was there for specific heat as well. Same definition is here for heat capacity as well. What is the difference? Now we'll understand it. The difference between heat capacity and specific heat is very, very important. So I will be repeating it 2 times. So you should be understanding it very. Heat capacity is a measure of a particular substance. Okay. So how much heat we are giving it to basically increase the temperature, or I can make it easy that it depends upon the amount of the substance. Whereas if I'm talking about specific heat is basically what? It is all about per unit mass, whereas it is independent of a amount of substance. That is, if I define specific heat for water, that specific heat of water, you can use it anywhere you want, whenever you want, wherever there is a question related to water, you can use it, because it is kind of a density. When I say density of water, it's 1000. So if you 1000 kg per meter cube, so it's like the formula, sorry, this density, if you want to use this density, let's say if you want to use this density for seawater or normal water, although there will be small difference, but you know that water is water. Same thing goes for specific heat. We specify specific heat for a certain material, not for the amount, whereas heat capacity is defined for a certain amount of the body, and that amount is replicated like this. That is, if you multiply the mass of the body with the specific heat of the body, you will get the heat capacity for the body. That's it. Very important. Next is the principle of calorimetry. This is very easy. Even if I don't tell you, it's like a fancy word for a basic thing. But when I'm talking about an insulated mixed system, so the amount of heat energy lost is actually equal to the amount of heat energy gained by the cold body. Okay. So it's very, very important. Now, you have learned it in smaller grades that if you want to change the physical state of matter, if you want to go from solid to liquid, liquid to gas, gas to solid, then you can either change temperature or you can change pressure. There are two methods to do it. We will be talking about both of them. So by changing temperature, we learn about melting point, boiling point. Okay. By changing pressure, temperature, we also learn about the concept of latent heat of fusion, as well as the latent heat of vaporization. Now, if you remember it, okay. If you don't remember it, I will just give you the understanding by this particular graph. This is the best way of understanding it. As you can see in this graph, what is happening? This is the heat axis. This is the temperature axis. What are we doing over here? That if we are increasing the heat, then clearly you can see that temperature is increasing in this region. I will repeat. By increasing heat, temperature is also increasing from region A to B. So you can say you took ice to minus 20 to minus 0 degrees Celsius. Okay. You took ice from minus 20 degrees Celsius to 0 degrees Celsius. And this is what is happening for ice. Okay. Now, but if you will see the second stage, if you will see the second stage, that is from point B to point C. If you are going from point B to point C, the temperature is not changing. Although we are increasing the amount of heat, heat is increasing, but temperature is not increasing. But what happened during this process? From 0 degrees Celsius to 0 degrees Celsius, you went like this. Okay. You can clearly see this is also 0. This is also 0. Okay. Now, water. Yeah. So you have actually converted what? Ice at 0 degrees Celsius to water at 0 degrees Celsius. So yes, we agree that temperature is not changing, but something changed. And what is changing? That is the state. So you can say, just like in this process, the amount of heat we actually give to the system goes on increasing the temperature. Exactly in the same way, in this particular setup, the amount of heat we give to the system goes in changing the state of the matter. You are not increasing the temperature or decreasing the temperature, but you are changing the state. You are converting ice to water. This is known as latent heat of fusion, because this is for ice water. So this is fusion. Okay. Whereas again, in this setup from 0 to 100, you will see that we are taking water at 0 to water at 100. So of course, again, we are increasing temperature and increasing heat, and the temperature is also increasing. Yeah, or we can say the opposite actually. We are increasing temperature and the heat is also increasing. But again, it gets stuck in this region. Why is it getting stuck in this region? Because when we actually took water from 0 to 100, from 0 degrees Celsius to 100 degrees Celsius. So during this process, the amount of heat we were giving went in increasing the temperature. But in the last state, as you can see, we are converting water into steam. You can clearly see. So finally, what we can say, during this process, again, you are giving heat, but that goes in changing the state of the matter. Okay. This is known as latent heat of vaporization. Vaporization is used for converting liquid to gas and all, whereas fusion is used for solids and liquids. Okay. Okay. So this is the whole setup we just learned. And now we also need to understand how will you calculate the value of heat. So if you want to calculate the value of heat in this process, we just learned we will use the concept of specific heat MC delta T, because there is clearly a change in temperature. So I will use MC delta T, we will get our answer. Similarly, if I want to do in this way as well, Q will be equals to what? MC delta T, because there is clearly a change in temperature. I can calculate the answer. But what about this particular setup? The value of Q will be equals to ML. And over here as well, Q will be equals to ML. Why? Because you can see there is no change in temperature. Of course, you cannot use Q is equals to MC delta T. But what is this formula? This is the just like the value of C over here means the specific heat. The value of L over here means the latent heat. And again, it is also having a fixed value. How? As you can see, there is a question over here. Very easy, but if you will read it properly, you will see that specific heat of ice, specific heat of water, then the latent heat of ice and latent heat of steam is also given. So latent heat is also kind of a number which we can easily, like, it's kind of a constant, you can say, just like C. That's it. Okay, let's have a look onto this particular problem over here. So if you are converting ice from minus 12 degrees Celsius to steam at 100 degrees Celsius, how will you actually calculate the heat required? So this question is lengthy, but don't worry about it. We will do it in steps. So if I want to convert the ice from minus 12 to 0 degrees Celsius, the heat will be what? MC delta T. Okay. So heat will be MC delta T, and I can easily calculate because mass is clearly given. Okay. That is 3 kg. The C for ice, specific heat of ice, is also mentioned. We can easily calculate this. Second thing, heat required to melt ice. Now if you want to convert ice to water from 0 to 0, as you cannot use specific heat now, you will use ml now. Okay. Next is converting the water from 0 to 1000. Okay. So water, like I will again use MC delta T over here, and okay. So if I want to convert water from 0 degrees Celsius to water at 100 degrees Celsius, again, I can use the specific heat formula. But for the last case, that is converting water from 100 to steam at 100, I will use ml. That is what we call as the latent heat. So what can we say finally? That if I want to calculate the overall heat of the body, I will do what? Q1 plus Q2 plus Q3 plus Q4. So in the 4 steps, the amount of heat required is this. I will add them. I will get the overall heat. Now this question will not come in your exam, of course, but we have made multiple segments of the question, and any one part can be there and it can be very easily done now. Okay. Last thing is thermal conductivity. So of course you have a rod. Imagine if you have a rod and it is heated from one end. So how quickly the heat will go onto the other side, or like how the heat will travel to the other side, it depends on multiple things. That is, it depends on the area of the face you are talking about. Either you are taking a thick rod or a thin rod. It first depends on that. Second thing, it depends on the temperature difference. How hot is this face? How cool is this face? Bigger the difference, far, like more the heat transfer. It also depends upon the time for which you have applied the heat. Like if the heat is being transferred for 1 second only or 1 hour, it depends on that as well. Then of course it depends on the thickness, like how thick is your rod. Last thing is the nature of material. What type of material are you using? So that type of material will be replicated by this constant K over here, which is the coefficient of thermal conductivity. What we have done, we have actually added all the things. That is, we have A, T1 minus T2, Tx, everything we have added, and the K is the telling you the type of given material. Okay. Okay, so the question based on these topics will be very, very easy. As you can see, like you just have to identify. Yeah. So there can be a different type of question. I can show you. It will ask you the rate of loss of heat. Now, whenever we use the word rate, it is talking about time. So how much time goes on in a how much heat goes on in a given amount of time? That is, of course, rate of loss of heat. Hmm. Yeah, like we are taking this particular time, we are putting it over here, and if we do something like this, oh, hmm. Now to calculate the rate of loss of heat, I will do Q by T, which is all the remaining things. Now all the other things are given in this question, that is area, X, change in temperature, and the coefficient of thermal conductivity of glass. As I told you, it depends upon the type of material you are using. So it will be given because it's a constant. So that's it for today. This chapter is not done. We will complete it in the next class. Till then, bye bye. Thank you so much. Bye.